In a previous video, we looked at essentially what a Riemann sum is, and then how to construct the Riemann sum, and we gave some notation associated with the Riemann sum. I'll just go ahead and give one of those notations, and then we'll do a couple examples to see how we actually find these sums. So remember, so the idea is we have a function and we have an interval on our x-axis, a to b. We're going to be given a number, excuse me, a number of partitions. So how many subintervals are we going to use for this approximation? So this is the number of subintervals, and then we have to have the type of Riemann sum, and the three typical types are where we use the right endpoint, the midpoint, or the left endpoint of each subinterval. All right. Okay. And then the idea is that the area is approximately equal to this sum. So I'm not going to go back through, deriving this, but you can watch the previous video and see how this formula and what everything means, how does it come about? So that's basically our formula for our Riemann sum or Riemann approximation, and that's going to approximate the area that we're looking for. And I'll just say where the delta x, and we also came up with this formula, is b minus a over n. All right. Okay, so let's look at some examples of how this can be done, and we'll do a couple examples. Maybe we'll do one example where we illustrate using the right endpoint, and then do the same example illustrating how we would use the left or the midpoint, right? Okay, so let's take this as our function, the natural log of, let's say, x plus 1. Let's take that as our f of x, and let's take our interval, let's take something simple, 2 to 5. And in practice, when you're asked to actually compute these Riemann sums or approximations, the number of subintervals tend to be small. So let's make this not too small to where you kind of lose the pattern to see what's going on, but certainly not large that we get overwhelmed by how tedious the amount of calculations is. So let's just take something like n equals 3. So we're just going to use 3 subintervals, and for our first example here, let's do the right endpoint. So let's use a right Riemann sum. And again, if you're wondering where does the name Riemann come from, it's the last name of a German mathematician, Bernhard Riemann. He was the one that you can thank him for a lot of the work that goes into this stuff, and a lot more for that matter. A really brilliant mathematician. Okay, so how do we go about working with this formula right here, right? Well, since it's essentially dependent on the subintervals, I always illustrate the steps in a process by first drawing this interval. So basically just a portion of the number line going from 2 to 5. And then based on this, I'll know how to split it up, right? So let's compute our delta x. So delta x in this case is 5 minus 2 over 3. And that's why I chose these numbers, so that at least in our first example, the delta wasn't something that's too cumbersome to work with. But regardless, whether these are integers or proper fractions, it's just numbers, so we could work with it anyway, right? Okay, so here's our delta. So that means we're going to break up the interval 2 to 5 into 3 smaller subintervals of length 1. So what that basically means is I'm going to go from 2 to 3, 3 to 4, 4 to 5. So it will look something like this. Right? So this is the subinterval. Notice I haven't sketched the graph. I guess in a second I can sketch the graph to kind of show you what this area is going to look like. Maybe we'll do it at the end. But also remember, we're not finding the exact area now. We're just doing an approximation, right? So really all we need to apply this formula, which looks really scary sometimes, we need to know which of these x values to choose. And then we're going to have to find the function value at those values of x, and then just do a sum, right? Okay, so if we're using the right Riemann sum, right, what it means is from each of these 3 subintervals, and we can see them, 2 to 3, 3 to 4, 4 to 5, we are going to choose the right endpoint. Right? So you just have to know the difference between your right and your left. So in the interval 2 to 3, and what I'll do is I'll mark it off with a red X here. So we will need that value of X, right? And then for the interval 3 to 4, the right endpoint is 4. And then for the interval 4 to 5, the right endpoint is 5. Now, an important thing is this n, not only does it allow you to compute the delta, which we obviously need, but it tells you that the selection or the number of x's, right, that you select to form this approximation has to be that same number. So if the question tells you to use 3 subintervals, you should see 3 subintervals, and I can see the 3 of them here, 2 to 3, 3 to 4, 4 to 5. And then out of each of those 3 subintervals, you're going to choose 1 x. So in total, you should have 3 x's that you're going to work with when we apply this formula. All right? So now I'm not going to write down the sigma form of the formula. The sigma form is good when you're trying to do something generally, but when you're trying to apply it to a specific function and interval and case, a specific problem, the sigma notation, you might say it's overkill. It's too much for what I need to do, right? So here's how you can write it out. So the area is approximately, so let's do this part first. So this says take the function value and then evaluate it at those special values of x. And those special values of x have been indicated by these red x's. So in other words, this is actually your x bar 1. This is actually your x bar 2. This is actually your x bar 3. So I'm just going to plug the first one of those. So 3, so this will be f of 3. And then the formula goes on to say I have to multiply it by delta. Well, it turns out, you have a delta of 1. I'm still going to put the 1 there so we're clear as to all the steps that go into using this formula. But we know that multiplying by 1 isn't going to affect this term. And then we repeat this pattern for the remaining x values, and then we do the sum. That's what our sigma here is saying. So it's going to be plus, and then the next x value is 4, so f of 4, again, times 1, that's my delta, and then plus f of 5. This is the final one, and then times delta. Another good thing to keep in mind is how, again, this number tells you how many terms are supposed to be in the summation, right? So if your n is 3, then you should see 3 function values here, right? So now we're going to get into the actual evaluation. So let's do this. So it's equal to, so now what is our function? Our function is the natural log of x plus 1. So wherever there's an x in this function, I'm going to substitute the value 3. So that will be the natural log of 4 times 1 plus, and then f of 4, that's the natural log of 5 times 1. And then finally, f of 5 is the natural log of 6 times 1. Now I really didn't need to write the times 1, so what this Riemann sum comes down to be is the natural log of 4 plus the natural log of 5 plus the natural log of 6. And then this is where you'll get out your computing device, whatever type of calculator you're using. And so I am gonna assume you know how to evaluate the natural log on your calculator. So I'll say that this sum comes out to be, and you can verify this, I encourage you to do that, is 4.78. I'm gonna write all the digits that my computing device gives me, and 742, and then it goes on, right? Because these are irrational numbers. They have a non-terminating, non-repeating decimal expansion. So this is the approximation of the area. Now notice we went through the process, we came up with this number without even knowing what the graph looks like, right? But many of us are visual learners, so it would be nice to say, okay, well, what does this really mean? So I am going to just give a quick sketch of this function, the natural log of x plus 1. Now you might remember the graph of just the regular natural log of x. It has a vertical asymptote at along the y-axis. But with let me rewrite it here. But with the plus 1, this plus 1 gives us a horizontal shift of 1 unit but to the left. So it has a vertical asymptote right here. This is the line x equals -1. And then the graph does something like that, right? So this is the graph, and so this is 0, here is 1, 2, 3, 4, 5. So the interval in this question was 2 to 5. And so the region whose area we just approximated, so this is right here. So what we can say is, based on this type of Riemann sum using this many subintervals 3, so this area is approximately, remember it's not exact because we're actually using rectangles to approximate what we have here. So this is approximately 4.7, I'll round to 2 decimal places, so 4.79 square units. I'll just say unit squared of area, right? And that's what this number means. So if you graph your function, indicate your interval, and then draw those vertical line segments up to the curve, that region there has an area that's approximately equal to this number, right? Let's use the same example, but now use a different type. So let's use the midpoint, right? So if we're going to use the midpoint approximation, let's see what it looks like. So using a midpoint approximation, well, what's going to change? Well, the only thing that changes when you change just the type of Riemann approximation that you're using is your x bars, right? So let me draw the interval again. I remember we're going from 2 to 5, right? And I guess I don't need this little part here. I don't need that part there, right? But now, instead of choosing, this would be the left, this is the right that we just used. In order to use the midpoint, then I would essentially have to find the average. What number is right here? What number is right here? What number is right here? And I'll do a little, I'll just give you the calculation off to this side, but you could probably tell without doing any kind of calculation what is the midpoint of this interval, right? So our x bar 1 in this case, it would simply be the arithmetic average of 2 and 3. So it's the midpoint. And if you remember from, basic algebra, how do you find the midpoint of something? Well, numerically, you add the endpoints together and then divide by 2. So we get 2.5, right? So that's what this first x value is. And then what I'll do I'll do x2 with the calculation again, and then I'll say something that will give you, once you have the first x, it will give you a nice easy way to generate the other x's that you need. So x bar 2 is the average of 3 and 4. So the 7 divided by 2, that's 3.5. So that would be the second x that we will need. Now if you notice, because of how this formula works, not only are these endpoints equally spaced, but the midpoints would then have to be equally spaced. If you think about it logically, it makes sense, right? If the subintervals are equally spaced and you're finding the midpoint of each of them, then the midpoints would have to be equally spaced. Not only that, but this here has the same delta. This delta is 1. If you take the difference between 3.5 and 2.5, you'll get 1, which means the difference between this x or next or third x and the second x would also have to have a delta of 1. So the easy way for me to find this, I could go ahead and do another average. But if I took this midpoint and then added my delta, then I would get the next x that I would have to choose. So I know for a fact, and it makes sense when you look at the number line, and if we're taking the midpoint of the interval 4 to 5, then it has to be 4.5, right? So these are the x's. Again, let me just write this down for completeness. We have that. And then let's go ahead and actually do the calculation, right? So these are our special x's. So our area is approximately, let me write it down symbolically now, it's going to be f of 2.5 times our delta plus f of 3.5 times our delta. Our delta is 1. And finally, f of 4.5 times our delta. So now we're going to plug 2.5 into our function. Remember what our function is. It's the natural log of x plus 1. So I have to take this x and add 1. So this now is the natural log of 3.5. Don't need to multiply by 1 because it's not going to change that function value. Plus the natural log of 3.5 plus 1. We have to remember to do what our function says because it's the function that gives us the height of each of those rectangles, right? So then this is 4.5, and the last term in our Riemann sum is the natural log of 4.5 plus 1, so that's 5.5. And again, you can verify this just so that you're evaluating things correctly, and this comes out to be 4.461588457. I said 5, but I wrote 7. Do as I say, not as I do type thing. And then so 4, 5, 7, and then again it goes on indefinitely, right? So that's the approximation if we use the midpoint method. And look at the two numbers, right? You know, this one up here is based on the right endpoint, and this one is based on the midpoint, right? Which is better, which is worse, we don't know, right? This is not the type of course where we analyze the accuracy of the approximation. We're just looking at how to find the approximation. All right, so there are two examples of actually computing these Riemann sums, just to give you an idea of the steps that are involved. But when you look at the actual calculations, it's very simple. It just comes down to making sure that you're using the correct x value and you're evaluating your function, multiplying your delta.